All right, let's go ahead and get started. So we're going to start off with this function. We're going to plot 3 points just to illustrate a point. So to find the points I'm going to plot, well, let's see. F of 1 is 1 cubed minus 1 minus 3, which is negative 3. And F of 2 is 2 cubed minus 2 minus 3, which is 8 minus 5, which is positive 3. So if we plot both those points, let's see, we have the point 1 comma negative 3 and 2 comma positive 3. And what I want to really point out here is that if you were to graph this function, since it is continuous, and we know it's continuous because it's a polynomial, and polynomials are continuous everywhere. Since it's continuous, there's no breaks. And so when we're graphing it, it's going to do something like this. And I don't really know what's happening after either side, but I know between 1 comma negative 3 and 2 comma 3, we're gonna hit every y value between negative 3 and 3. Specifically, we're gonna hit 0. So the actual kind of question that I didn't ask here was, what we really want to do is show that this function, x cubed minus x minus 3 equal to 0, has at least one solution. And it does. What we can see here is that, oh, well, f of 1 is certainly negative. F of 2 is certainly positive. And since the function's continuous, you have to get from every y value that goes from negative 3 to positive 3 and everything in between. So specifically, there must be some input between 1 and 2 we usually call it C, such that if you input C into that function, you get out 0. So somewhere between 1 and 2, I don't know what it is, but there's some number between 1 and 2 that if you plugged it into this x cubed minus x minus 3, the output would equal 0. This is the very essence of the intermediate value theorem. Sorry, I'm looking for pens here. 1 second. We're not the right one. You can send off the other one. Okay, so more generally stated, here's the idea. Yeah, sure, we'll do it that way. I can't see very well over here. Let's put you over here. So let's draw something first. Let's say so we have some graph on the x-axis, y-axis. You've got some function, let's say, starting here and doing something kind of like, I don't know, like that. So we'll say that's our A there. That's our B there. This output is F of A. And this output here is F of B. And as long as your function's continuous, which it certainly appears to be from the way I've drawn it, we have to be able to get every y value between F of A and F of B for using some x value that lives between A and B. So here's kind of the formal statement of the intermediate value theorem. If f of x, which is what we're calling this function, is continuous on the closed interval from A to B, and n is any number between f of A and f of B, then there exists at least one, but there might be multiple, at least one number which we call C. C lives between A and B, such that f of C is equal to that number n. Graphically, it looks like this. Pick some number between f of A and f of B. Okay, I'm picking that number right there. Then I should be able to go over to my graph and say, oh, look, there's some input between A and B so that f of C is equal to n. That's the whole idea. Or in other words, stated more simply, if your function is continuous, you get all the y values between two y values. That's the whole deal, really. Most of what we do with the intermediate value theorem is use it to show things like the first thing, where we show that that polynomial equal to 0 had a solution. We didn't find the solution. We just showed that there was a solution. That's kind of it. Let's say one more thing about the intermediate value theorem, because that's kind of all there really is to say. So let me show you one more example involving the intermediate value theorem. Sorry, I keep looking at my pens like they're going to change. Ill prepared here. So here's another type of intermediate value theorem question. Show. Yeah, I just need to stop using terrible pens. I'm sorry. Come better prepared next time. Show that f of x equal to x cubed plus x squared plus x minus 10 equal to 0 has at least one solution between A equal to 1, B equal to 2. Welcome, Dan Land. Dependence orange in front of you. So, if this was a question, I know everyone just finished their first exam or a while ago, but like, right, we're done with the first round of exams. A question like this probably didn't show up on your exam, but it could show up on your next exam. So let me show you how I would answer this as an exam question. I would do the following 3 steps. Step 1, I'm going to evaluate f of A and f of B. The hope is that one of these values is less than 0 and one of these values is bigger than 0. So the 0 is stuck in between them. Let's see. F of A is going to be f of 1, which is 1 cubed plus 1 squared plus 1 minus 10, which is 3 minus 10, which is negative 7, which is less than 0. On the other hand, f of 2 is 2 cubed plus 2 squared plus 2 minus 10, which is 8 plus 4 plus 2 minus 10, which is 4. So that's my first step. I got f of 1 is negative, f of 2 is positive. And then you should say something about how the function is continuous on the interval. Really, you just have to kind of just say it. Yeah, okay, observe or note or whatever you want, word you want to use to point it out. Note that f of x is continuous. It only needs to be continuous on the interval we're working over, but it's welcome to be continuous on a bigger domain. This function is continuous everywhere because it's a polynomial, but certainly on the interval from 1 to 2. And then the third part is kind of summing up what we want to say. Since f of 1 is negative and f of 2 is positive and f of x is continuous, by the intermediate value theorem, which we almost always abbreviate as IVT, there must be some C. Where does C live? Between what two numbers? That's where the output's going to live, between -7 and +4. But the input has to live between these two inputs. So it's going to live between 1 and 2. So there's got to be a number C. I usually write like 1 less than C less than 2, such that f of C is equal to 0. If you go from negative to positive, you have to hit every number in between, and 0 is certainly one of those numbers. Questions about this? It can be a little bit harder to do a problem like this if they don't give you the interval. For example, someone could ask you to show that, I know I said one more, but show that, let's do it that way. Sure. X squared, I don't love that choice, James, equal to cosine of X has a solution. Ugh, that seems terrible. A couple things. Thing one, I might just graph it to see where things might be working out. What do I mean by that? Well, X squared looks like this. Again, vaguely. And cosine, looks like this. So it looks like there's probably actually two solutions. One over here that's some negative number, one over here that's some positive number. We're only trying to find one of them, so we can pick or choose. I'm going to go on the right side because positive seems easier. So I'm going to think, well, it certainly looks like the red function's bigger at 0, and it looks like the blue function's bigger somewhere over here, like where cosine of pi over 2 is equal to 0. Right, that point there is pi over 2. But I'm really getting ahead of myself. What I should actually do first is make my life easier. Instead of trying to show that this has a solution, we're going to rewrite it. You almost never want to show that two things are equal to each other somewhere. You want to show that something is equal to 0. It's almost always easier. So if you're ever trying to show some equation has a solution, rewrite it or reframe it so that we're thinking of trying to show that x squared minus cosine of x equal to 0 has a solution. And I'm making an educated guess here. I'm pretty sure that this is going to be one sign at 0 and a different sign over here at pi over 2. Well, let's check. So what we usually do at this point is we're going to say that our function f of x is x squared. Let f of x be x squared minus cosine x. That is not how you ever write that. Well, let me try that again. Here's the smarter way to write that. Let f of x equal x squared minus cosine of x. That is the normalish way of doing that, not what I wrote before. We're going to check two things. We're going to try f of 0. Okay, f of 0 is 0 squared minus cosine of 0, which is 0 minus 1, which is -1, which is certainly less than 0. And I'm going to try f of pi over 2. F of pi over 2 is pi over 2 squared minus cosine of pi over 2. I know that cosine of pi over 2 is 0, so I'm going to get pi squared over 2 squared minus 0, which is just pi squared over 4. I don't know exactly what that is, but I know it's positive. Pi is bigger than 3, pi squared is bigger than 9. 9 over 4 is certainly a positive number. The second part here, which we definitely need to state here, is note that our function f of x equal to x squared minus cosine of x is continuous everywhere. How do we know this? Because we know that polynomials are continuous everywhere, and sine and cosine are also continuous everywhere. And if you add or subtract two continuous functions, you still have a continuous function. Thirdly, this is where I always feel like I write too much personally. We should try to be a little bit more succinct. I'm a little too wordy sometimes. We can say by the intermediate value theorem, right? We don't have to restate the things we already did. There must be a number C between blank and blank such that f of c equals 0, which shows x squared equal to cosine x has a solution. Where does c live? Is it between -1 and pi squared over 4, or is it between 0 and pi over 2? 0 and pi over 2. There's some place, which I know I've kind of labeled this poorly here. That's the pi over 2 part. That part right there, that's where your c probably is. Somewhere a little bit less than pi over 2. But yes, our c lives between the x values that we picked. And that's pretty much the gist of the intermediate value theorem, is saying that if the function is continuous, you get all the y values. If it's not continuous, you're not guaranteed to get all the y values between two y values. No. Okay. Yeah.
Is it fair to say that if one is greater than 0 and one is less than 0, then it's continuous?
No, not at all. So for example, I'm trying to think of an example now. The problem is coming, so sure. So let me point out, if your function was, say, like, I'm gonna pick something very straightforward. If your function was f of x equal to 1 over x, and certainly I will point out that f of 2 is 1/2, which is greater than 0, and f of -2 is 1 over -2, which is -1/2, which is less than 0. But I can't say that this thing has a solution equal to 0, right? I will observe f of x equal to 1 over x equal to 0 does not have any solution. And the reason this isn't violating the intermediate value theorem is because that function isn't continuous on the interval from -2 to 2. Right? If you were to graph that, we know that f of 2 is 1/2, right there, and f of -2 is -1/2. But then the behavior of this function actually looks like this. You go down that way, and then down that way. So because the function has a discontinuity on the interval, we're not guaranteed to get all the y values between those two y values. Yeah, good question. Thank you for asking that. It's definitely an important thing to do. You have to have all the conditions met to then use the theorem. That's all I really have to say about the intermediate value theorem. Unless there's other questions about it, you're welcome. But let's move on and start getting into stuff about the derivative. So, yeah. Trying to keep track of things, James. So here's the beginning problem. Let's find the slope of the function f of x equal to the square root of x at x equal to 9. Let's draw a picture. My square root function. And kind of So let's say that 9 is right here. We want to find slope of that tangent line. Well, as you might have seen already, it's kind of challenging to find the slope of a line if you only have one point. We don't really know how to do that yet. This point here, by the way, would be the point 9 comma 3. So our function is f of x equal to the square root of x. So our beginning idea is that instead of finding the slope of the tangent line, we're actually going to grab another point on the graph. Let's say that that's, and there's lots of ways of doing this. I usually like to use the h notation. So I'm going to say that this is 9 plus h. So I've added on a distance of h here. And I'm going to find the slope of the secant line that goes through these 2 points on my graph, which I did not draw very well at all. Shame. Oh my gosh, that's terrible. I feel a little terrible. I feel like I need to try it again because it's really bad. Sorry. Sometimes you win, sometimes you lose when you're drawing graphs, and I definitely did not win on that one. Let's try one more time. So let me draw the secant line first. That's actually usually the better idea. So here's that one. That one. So if I draw the secant line first, this is where I really should have my ruler with me, but I do not. That is much better. So there's my secant line going through the point 3 comma 9. And point over here, which has an input of 3 plus h, an output of 3 plus h. Sorry. Now I'm just mislabeling things. My function is what? Let me rewrite this here. Find the slope of f of x equal to the square root of x at x equals 9. So I mislabeled this point here. Shouldn't be 3 comma 9. It should be 9 comma 3. So I'm inputting 9 and out 3. Same deal here. This shouldn't be 3 plus h comma 3 plus h, whatever. This should have been 9 adding on h. It's 9 plus h. So that point right there is 9 plus h comma the square root. 9 plus h. Apologies for the mistakes. So then to find the slope of the secant line, usual slope fit. Find the slope of any line between 2 points, you just take the difference in the y's divided by the difference in the x's. So that's going to be our y2 minus y1 for x2 minus x1. Or if you prefer, you can write it as delta y, delta x. In this case, it's going to be that y value minus that y value. So the square root of 9 plus h minus 3 divided by that x value minus that x value. 9 plus h minus 9. Which we can certainly simplify to be just the square root of 9 plus h minus 3 divided by h. Now here's the crux of this whole process. To find the slope of the tangent line, we're going to let that point move closer and closer to that point. So like if we moved over to say, let's use a different color here. If we moved over here, and now this was your smaller h value, and this was 9 plus h, and then we use the point up there, our secant line would have a slope that's closer to the slope of the actual tangent line. And as we let h approach 0, the slope of the secant line approaches the slope of the actual tangent line. So, for a tangent line, which I didn't draw again, sorry. But to find the slope of our tangent line, we're going to say that it's equal to the limit as h approaches 0 of the slope of our secant line. Or written kind of with more words, slope of the tangent line equal to limit as h approaches 0 of the difference in the y's divided by the difference in the x's. Which you might notice if we plug in 0, we get a 0 over 0 type of limit. This is the main reason we spent so much time talking about 0 over 0 limits, because they are always what shows up when you try to find the slope of a tangent line. So to deal with this, well, let's see, I see a square root, so I'm going to multiply the top and bottom by the conjugate. So we're going to rewrite this as being equal to the limit as h approaches 0 of the square root of 9 plus h minus 3 h times the square root of 9 plus h plus 3 over the same square root of 9 plus h plus 3. Just like before, we multiply out the things that are actually conjugates. So we're going to have the limit as h approaches 0. On top, you're going to get the square root of 9 plus h times the square root of 9 plus h, which is 9 plus h. The middle terms cancel out, and then we get minus 3 times 3, which is minus 9. In the denominator, we don't multiply anything. We just leave it as h times parentheses square root of 9 plus h plus 3. Why don't I multiply it out? Because I'm hoping that that h, that first h in the denominator, I really want that to get canceled out. Because that's the thing that's making me divide by 0. So if that h can get canceled out, I'm in good shape. And that's almost always the case for these slopes of tangent lines. You're trying to get to a place where that original h in the denominator gets canceled. And it's going to. The 9 subtract, 9 minus 9 is 0. And then we have the limit as h approaches 0 of h divided by h times the square root of 9 plus h plus 3. And then h divided by h is 1. So we have the limit as h approaches 0 to 1 divided by the square root of 9 plus h plus 3. And now that we have dealt with the problematic h, we are good to substitute in h equal to 0 for the rest of the h's. So then we can just plug in 0 for h and get 1 over the square root of 9 plus 0 plus 3, which becomes 1 over 3 plus 3, which is 1 over 6. That is the slope of the tangent line to this graph at that point. Now, the downside of doing it this way is then if I were to ask the question, what's the slope of the tangent line at a different point, say like at x equal to 16, we'd have to do all this work again. And every time I asked for a different point of tangency, we'd have to go through this process of taking a limit, multiplying by conjugate, so on, so on, so on. So what we usually end up doing right away is saying, instead of finding tangent lines at particular points, we're going to find slopes of tangent lines at kind of any point, just based on the slope of the tangent line being a function of the value of the limit. So let me do another example. But now we're going to be more broad about it. So let's say we want to find the slope of any line tangent to the function f of x equal to x squared plus 6x plus 1 at a generic point x comma f of x. And again, we don't really need a graph here, but I still like drawing it to kind of see what's going on. So we've got some parabola, looks, I don't know, vaguely like this. It might not look quite like that, but I don't care so much about what it looks like. And the idea is we would really like to find the slope of the tangent line at the point right here. But we're just going to say that that point is the point x comma f of x. Some x value, it's got some y value. And then we're going to apply the same sort of thinking we did last time, where we're going to move over a little bit to say x plus h. So that this point here is x plus h comma f of x plus h. And first find the slope of the line that is the secant line that goes between these 2 points. So the slope of that green line that goes from x comma f of x to x plus h comma f of x plus h is going to be, well, again, your change in y over your change in x is going to be the difference in the y's. So f of x plus h minus f of x divided by the difference in the x's, which is x plus h minus x. And then just like before, to make that secant line slope get closer and closer and closer to the slope of the tangent line, we're going to let the x and the x plus h point get closer and closer to each other. So we're going to let h get smaller and smaller and smaller. So to find the slope of our tangent line, we're going to take the limit as h goes to 0 of f of x plus h minus f of x divided by x plus h minus x is going to be just h, regardless of what value of x we have. And this is how we always find the slope of a tangent line. It's the limit as h goes to 0 of this expression over here, which is called the difference quotient. So for this problem, that's going to be the limit as h approaches 0 of, let's see, so f of x plus h is going to be x plus h squared plus 6 times x plus h plus 1 minus f of x is going to be just x squared plus 6x plus 1 divided by h. And at this point, if we plugged in h equal to 0, you should be able to see that it's going to do the same thing it would have done before. We're going to get 0 over 0. Because if h is 0, we have x squared plus 6x plus 1 minus x squared plus 6x plus 1, which is 0 over 0. So always with these difference quotients and taking their limits as h goes to 0, we always have to do some sort of algebraic thing to manipulate them to get the thing, to get that h, the first original h in the denominator, to cancel out. So whenever you see this, you should be like, I have a goal. And that goal is to make that first h in the denominator cancel out. Any other h to stay behind is fine, but that one right there is the problem. So we're going to deal with that one. So we're going to multiply at the top. We're going to take the limit as h goes to 0. X plus h squared FOILs out to x squared plus 2xh plus h squared. Distributing the 6, we get 6x plus 6h plus 1. Distributing the minus sign, we get minus x squared minus 6x minus 1 divided by h. Now we cancel some things. The positive x squared and the negative x squared, the positive 6x and the negative 6x, the positive 1 and the negative 1. What should happen, and this is usually an intermediate step that I look for, is that once you've canceled stuff in the numerator, every remaining term should have an h in it. And they do, 2xh, h squared, and 6h. And if that's the case, which it should be, we can factor out an h. So we can say, hey, that's going to be the limit as h approaches 0 of h times 2x plus h to the first plus 6. Still divided by h. The h's divide to 1, and then we're left with the limit as h approaches 0 of 2x plus h plus 6. Then we let the remaining h's go to 0, and we get 2x plus 0 plus 6, or just 2x plus 6. So here's what this is telling us. This is telling us for any choice of x, the slope of the tangent line to the function x squared plus 6x plus 1 is going to be 2 times whatever x was plus 6. So for example, at the point, say, I don't know, 3 comma f of 3, which is, let's see, f of 3 is 9 plus 18 plus 1. So that's 3 comma 28. At that point, the slope of the tangent line is going to be, well, if we plug in 3 for x, we're going to get 2 times 3, which is 6 plus 6. Slope is going to be 12. And then I can ask a different point, and we just plug it back into that thing and do it right again, right? You don't have to keep deriving this slope every time you pick a new value of x. So why are we doing this? Well, because we're building up to the idea of the rate of change of a function, also known as the derivative of a function, which is calculated in this way. Let's do one more example before we get super definition heavy here. Yeah, let's look at this next one. So we're going to find slope of the tangent line to f of x equal to x over x plus 1 for any x. That's part 1, and then we'll have a second part 2 at the end. So, same idea as before. If they say slope of the tangent line, we know that we're going to find the limit as h approaches 0 of our f of x plus h minus f of x divided by h. And even though I didn't draw the graph, we're still imagining, oh yeah, this thing without the limit is the secant line's slope, and then we're just letting the points get closer and closer to each other so that we're getting the slope of the tangent line. That's always what we're doing with this. We're just going to stop drawing the picture because sometimes the pictures are really gnarly. So we have to be extra careful here. The limit as h approaches 0. Our f of x plus h is going to be, well, instead of x over x plus 1, we're going to get x plus h over x plus h plus 1. Right? Everywhere there was an x, we put an x plus h minus f of x, which is x over x plus 1, all divided by h. Yeah. Okay, so at this point we need, well, we have fractions and fractions, which means we probably need a common denominator. So what we have to do here is rewrite it. I'm going to do 2 things at once here. First thing I'm going to do, instead of dividing by h, I'm going to write it as multiplying by 1 over h so that I don't have to have 2 fractions. So it's going to be 1 over h times the stuff on the top, and I'm going to write it as x plus h over x plus h plus 1. I'm going to leave myself some space to multiply by something, minus x over x plus 1 times something. And some things I have to multiply by are, I need a common denominator. And if my fraction denominators are x plus h plus 1 and x plus 1, the common denominator is that times that. X plus h plus 1 times x plus 1. So we're going to multiply this one by x plus 1 over x plus 1, and this one by x plus h plus 1 over x plus h plus 1. And so, all right, so dividing that by h, we're multiplying it all by 1 over h, which is the same thing. Okay, so now we're going to simplify. Still have the limit as h goes to 0, still have our 1 over h out in front. This is the h we're looking to cancel out, that 1 over h in front. That was our original h in the bottom. So now this first fraction, if I FOIL out the top, I'm going to get x squared plus x times 1 plus h times x plus h times 1 minus x times each of these things. So I'm going to get minus x times x times h, x times 1. And I put the minus sign out in front, so I'll have to distribute in the next step. And the denominator, I'm not going to multiply it out. I'm going to have x plus h plus 1 times x plus 1. Most of the time, when you're dealing with these sorts of expressions, you rarely want to multiply out the denominator. You're usually not working with that part until the very end. So now we're going to simplify. The limit as h approaches 0 of 1 over h times. You can do this one of 2 ways. I'm going to distribute the minus sign, say I have x squared plus x h plus h minus x squared minus xh minus x, all divided by still x plus h plus 1 times x plus 1. Now we can say that x squared minus x squared is 0, x minus x is 0, and xh minus xh is 0. And the only thing remaining in the numerator has an h in it, which is a good sign, right? After we do our canceling, we want everything left over on top to have an h in it, and we do. This is equal to the limit, as h goes to 0, of h over h times x plus h plus 1 times x plus 1. Sorry, that looks bad there. Notice I didn't write 1 over h times my thing anymore. I just brought the h into the rest of the denominator. That's totally fine. And now the h divided by h is 1. We have the limit as h goes to 0 of 1 over x plus h plus 1 times x plus 1. And now we let the remaining h's become 0. We get 1 over x plus 1 times x plus 1, or if you prefer, 1 over x plus 1 squared. Whew, kind of a lot of work. Later on, we'll learn a much more succinct way of finding this thing. Second part of this question. What is the equation of the line tangent to f of x equal to x over x plus 1 at the point where x is equal to -3? Well, to find the equation of a line, we need two pieces of information. We need a point and we need a slope. So we need point, and we need a slope. We already have half of the point. They gave us the x-coordinate, but we need the y-coordinate. So our point is going to be -3, comma, whatever the y value is when we plug in -3 for x. Well, if you plug in -3 here, you get -3 divided by -3 plus 1, which is -3 over -2, or +3/2. And then we just found the equation for the slope of the tangent line at any value of x. So our slope of our tangent line is 1 over x plus 1 squared. So if we plug in x equal to -3, slope of our tangent line is going to be 1 over -3 plus 1 squared, which is 1 over -2 squared, which is 1/4. So great, I have all the things I need. And then I usually like to use the point slope form when I write the equation of my line, which is your y minus your y coordinate equal to your slope times x minus your x coordinate. So in this case, our equation is going to be y minus 3/2 is equal to 1/4 times x minus -3. I personally think it's fine to leave it this way. But some people like you to solve for y and simplify or stay with the y-intercept is. So if you write this in the y equals mx plus b form, we have y minus 3/2 equals 1/4 times x plus 3. Distribute the 1/4. That's equal to 1/4 x plus 3/4. And then we're going to add 3/2 to both sides. So we get y equal to 1/4 x plus 3/4 plus 3/2. And if you want to have those together, 3/2 is really 6/4. So 3/4 plus 6/4 is 9/4. So we could say in the y equals mx plus b form, our equation is y equals 1/4 x plus 9/4. In my opinion, either one of these answers is totally fine. But my opinion is not the one that counts. So you should do what the instructions ask you to do on the exam or on the website. Plus. Yeah. Yeah. Okay. So. Keep getting out of order. Apologies. So what we've been talking about this whole time without saying the words are what's called the limit definition of the derivative. So for a function f of x, we define the derivative of f of x to be f prime of x equal to the limit as h approaches 0, f of x plus h minus f of x, all divided by h. There are alternate ways of writing this. You might have seen something like f prime of x naught equals the limit as x naught. Sorry, it still is h approaches 0. Apologies. That looks terrible. Yes. Thank you. Of f of x naught plus h minus f of x naught all over h. Or you might have seen something like f prime of a equals the limit as x approaches a of f of x minus f of a for x minus a. These are all really the same sort of definition. They're just slight variations on each other. The idea really still being in any one of these cases, you're finding, say, the slope of a secant line between 2 points, and you can either label these points as almost. You can label these points as, say, x and x plus h, or x naught and x naught plus h, or, and this is where things get weird, a and x. So, whichever way you want to label this, right? If this is x and x plus h, then that's going to be f of x, and that's going to be f of x plus h, and the slope between these 2 points is f of x plus h minus f of x all over x plus h minus x, which is just h. Or, and really it's the same with x naught, right? If you use x naught, this would be f of x naught, this would be f of x naught plus h. Same idea. You're taking the difference in the y's, which is f of x naught plus h minus f of x, divided by the difference in the x's, which is just h, and then you're letting h get smaller and smaller and smaller, so the points get closer to each other, so we get closer to the slope of the tangent line. Finally, this last way of writing it is equivalent. This distance here, you could also think of as x minus a. And this distance here is f of x minus f of a. So you've still got the same difference quotient idea, and then instead of saying that h is getting closer to 0, we're saying that x is getting closer to a. We're still closing the gap, though, between those 2 points. I will point out that this is probably the way I prefer to write it, because it's usually the easiest computationally. Yeah. So let's look at some more. So, one second. That's not getting something there. So let's sketch the graph of the derivative from graph of the original function. Here's the first example. So there's our function f of x. Now I want to sketch the graph of the derivative. In other words, I want to sketch the graph where all the function values are now the slopes of the tangent lines of this function. So if I have to do this, what I usually focus in on is where the slopes of the tangent lines might be 0. So I'm going to point out that right about here, tangent line is horizontal, meaning it has slope of 0. Similarly, right there and right there. So if I'm going to try to graph derivative as a function of x, try and line things up. So I'm going to point there. There. So if I'm graphing the derivative, which is the slope, at those 3 points or those 3 x values, my derivative should be equal to 0. All right, so now let's take a look at what's going on in between things. So on the left side of this first horizontal tangent line, I can see that my slopes of my tangent lines are for sure going to be very negative. Right, this is a very steep negative tangent, and it gets less steep as we go further to the right. So we're starting off very negative and getting less negative. So maybe something like this. Starts off very negative, gets less negative. And then between here and there, our slope becomes slightly positive, more positive, probably the most positive, like right about there, and then tapers off and becomes less positive until it gets back down to 0. So we're going to do something like that. Right? More positive, more positive, more positive. The most positive it could be the steepest the slope is between here and here, and then less positive, less positive, less positive, back to 0. Same kind of deal between this point and that point. We're going to start off being slightly negative, the very slightly negative tangent slope, and then more negative, and the most negative, and then less negative, and less negative. Something like that. And then finally, after this one here, we can see that we're having a slightly positive tangent line slope, more positive, more positive. So we just keep going up and up and up. So the values of the derivative are the slopes of the tangent lines of the original function. Or another way of saying that, the values of the derivatives are the rates of change of the original function. Let's look at one more example. Yeah, I feel like, yeah, sure. So let's look at this example. Here's an example we definitely know. And we're still sketching things. So our function is the absolute value of x. So it looks like usual V-shaped function. So if I'm going to try and graph the derivative, well, this one's kind of even easier in that on the left side, what's the slope of that line? Question. What's the slope of that line? Lost points. 1, 3, -1, -1, 1, -3, 3. Well, it's a straight line for sure in this stuff. So the slope is constant. So whenever you have a straight line, your slope is always one number. In this case, our slope is -1 over here, right? If you go from that point to that point, you're going over 2 and down 2. And your rise over your run is 2 over negative 2 over 2, which is negative. So one way to think about this is, oh yeah, the slope on the left side here is just 3 minus 1. Sorry, yeah, 3 minus 1 over -3 minus -1. Which is 2 over -2, which is -1. And that's true everywhere on the left-hand side. So everywhere on the left-hand side, except at the origin, we're going to say that the slope is -1. And on the right-hand side, what's the slope on the right-hand side? It's not a surprise, it's going to be +1. But at the origin, what's the slope of the tangent line? Well, the problem there is I've got a corner, right? There's not just like a nice slopey thing that is beautiful and curved. It sharply turns a corner there, and we can't really draw any tangent line. Or you could draw a lot. Like technically, you could say that line is tangent, or that line is tangent, or kind of any line that goes to the origin would be tangent, which means we don't have a tangent line, which means the function's not differentiable at this point. Yeah.
Are the open circles intentional?
Yes, the open circles are intentional, because what we're saying here is that our derivative is a piecewise function. It's equal to 1 if x is greater than 0 and -1 if x is less than 0. But at 0, it is undefined. So I'll point out here that f prime of x, sorry, that's not what I meant to write. The f of x equal to the absolute value of x is not differentiable at x equal to 0. And we can see that because the graph is pointing. Usually I say something like the pointy points are where the function is not differentiable. Sometimes they're called corners if it's like a right angle turn like that, or they can also be called cusps, like in this next example. G of x equal to x to the 2/3 power. The graph of, ooh, that looks a little blurry. Okay. So this function looks like this. So points I would plot are the points 1, 1, 8, 4. It's kind of funky. On the left-hand side, -1, 1, -8, 4. Wow, this is best day for drawing things here. And at the origin, it's again super duper funky, right? It's pointy. It's not differentiable there. In fact, if you look at the tangent lines, again, my drawing is less than excellent here, but the tangent lines are getting steeper and steeper and steeper as you come in towards the origin. Like tangent line, really want to drop because I feel like my line's already good. Like right here, my tangent line's fine. But as I move in, they're getting super duper steep until right near the origin, they're getting closer and closer to being a vertical tangent line. And the slope of a vertical line is undefined. So the derivative there is not defined because the slope of the tangent line would be undefined. How do we show this? How do we show that g of x equal to x to the 2/3 is not differentiable? X equal to 0. Yeah, it's a big question. So one way to do this would be actually just define the derivative as a function of x and then show that it's undefined at 0. But we don't quite have the tools for that just yet, because finding the derivative of x to the 2/3 the long way is really kind of gross. So we're not going to do f prime of x equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, which ended up being the limit as h approaches 0 of x plus h to the 2/3 minus x to the 2/3 all over h. There is a way to do this. You have to multiply by something that's kind of like the conjugate, but it's worse. But here's the good news. If they're trying to show differentiability at they're trying to show function that's not differentiable or differentiable at a particular point, we can go back to kind of the earlier version of the definition and say, well, I don't really need to find the slope of the tangent line everywhere. I don't have to find f prime of x. I just have to show that the slope of the tangent line at 0 isn't defined. So here's what we're going to show. We're going to show that f prime of 0 does not exist or is undefined. Once again, the idea is going to be the same, right? We're taking the slope of a secant line. So here's one of my points, the point 0, 0. And here's my other point, h, f of h. So I'm trying to find the slope between those 2 points. And then we will see that as this point moves closer to the origin, the slope is going to get steeper and steeper and steeper until it becomes undefined. So here's what we've got. Notice right now how the definition I'm about to write is going to look very similar to this. I'm just going to replace the x's with zeros. So f prime of 0 is going to be the limit as h approaches 0 of f of 0 plus h minus f of 0 divided by h. So instead of finding the derivative at any value of x, we are specifically looking at the derivative when x is equal to 0. That's going to be the limit as h approaches 0. Let's see. 0 plus h is h. And my function, oh, sorry, I wrote f instead of g. Sorry about that. Terrible, James. This will change these to f's. It's so natural to just go back to f. I'm sorry about that. The day for mistakes, clearly. I also apologize for it. So instead of writing x plus h to the 2/3, I'm just going to write 0 plus h or h to the 2/3 minus f of 0, but f of 0 is 0 to the 2/3 power, which is 0, all divided by h. And if we simplify this, look what happens. We get the limit as h goes to 0 of h to the 2/3 divided by h to the 1st. And this is a time where I really recommend not writing it as a negative power. So I don't think it helps us a whole lot to write this as the limit as h goes to 0 of h to the negative 1/3. 2/3 minus 1 is negative 1/3. It can be really easy to convince yourself that that's just 0. It's not 0. If you rewrite it as the limit as h approaches 0 of 1 divided by h to the positive 1/3, then you say, oh, I'm plugging in 0 for h. The cube root of 0 is still 0. And then 1 divided by 0 is infinity or negative infinity, depending on which side we're coming at it from. In fact, if you're coming at 0 from the right-hand side, it's going to be positive infinity. If you're coming at 0 from the left-hand side, it's going to be negative infinity. So the overall limit actually does not exist. But that limit was the definition of the derivative at 0. So if that limit doesn't exist, the derivative doesn't exist, or the function is not differentiable at that value. So it is very, very true that f of x, again, sorry for the name change, equal to x to the 2/3 is not differentiable at x equal to 0. So where are we going? Well, we're heading towards talking about finding formulas or patterns for derivatives of various types of functions. Let's look at a couple of not terrible examples. Let's say there are a function, and I'll just call it f of x because eventually call it f of x. Say our function was 3x plus 2. It's a straight line. It is a line with a slope of what? This is so quiet. Say it. With a slope of 3. What that means is the derivative of this function is always 3. Or what I would like to say is that this function increases at a rate of 3, meaning for every 1 that x increases, the y value or the function value increases by 3. So your derivative here, f prime of x equals 3, is our rate of change. It represents how much f of x increases or decreases if it's negative when x increases by 1. So every time x increases by 1, y increases by 3. For this function, which is a straight line. Other functions, it's not always a constant rate of increase, right? Like for the previous one, our derivative was like 2x plus 6, and based on the value of x, your rate of change is going to be different. So I think for this function, you normally would be able to just say we know what the derivative is without going through all the work. But we could also do the work. We could find the derivative here by saying it's the limit as h approaches 0 of, I almost always like to write out this part, the f of x plus h minus f of x all divided by h, even if I know what I'm writing after that. I think it's good to show the person looking at your work, if it's a test, that you know what the definition is. And then we can jump to saying, okay, limit as h approaches 0. My f of x is 3x plus 2, so my f of x plus h is 3 times x plus h plus 2 minus my f of x, which is 3x plus 2 divided by h. I want to point out that whenever I do this, my f of x, I'm almost always putting in parentheses to make sure that the minus sign distributes to all the terms. Simplify. Limit h goes to 0 of 3x plus 3h plus 2 minus 3x minus 2 divided by h. Not surprisingly, the things that don't have h's end up canceling. 3x and negative 3x add to 0. 2 and negative 2 add to 0. So we're left with the limit as h approaches 0 of 3h divided by h. The 3h divided by h is just 3. And the limit as h approaches 0 of 3, well, the limit of a constant is always just that constant. So we can also just show, oh yeah, this function, it's a straight line, its derivative is the slope of that line. Or you could say it's the slope of the tangent line, because any tangent line, it's kind of weird. You talk about the tangent line of a line. A tangent line to a line is just the same line. If you take this line, right here, if this is my line y equals 3x plus 2, and I pick a point on it and try to draw the tangent line is exactly the same line. So I'm not going to draw it because it's already there. So we'll do that. So let's use limit definition to find f prime of x for the function f of x equal to x to the third power. We're going to do this limit definition stuff for a while, meaning like today and some of when we meet on Thursday and your classes for a while, but eventually we're going to move past it. Eventually we're going to learn some rules of differentiation, which we're kind of building up to right now. So if I want to find the derivative of x cubed, well, I'm going to start with the limit definition. So I'm going to say my derivative f prime of x is equal to the limit as h approaches 0 of x plus h to the third power minus x to the third. Now, if this were an exam question and they said use limit definition, even though you might already know that the derivative is equal to 3x squared, we still have to show this work. So if you're being asked to use limit definition, I really strongly recommend that you practice doing it because it's almost undoubtedly true that you will have a limit definition of the derivative question on your next exam. Very likely. Probably, yeah, usually one. So we're going to multiply this out. Okay. So x plus h cubed. I don't remember if we talked about Pascal's triangle in this class or not. Seeing faces that look like no. So I'm going to move away from this for a second. So there's a really cool triangle. It's like kind of the coolest triangle ever, actually. I mean, there's lots of cool. 3, 4, 5 is probably the coolest triangle ever. But a close second is Pascal's triangle, which is very different. Here's Pascal's triangle. And it's a triangle full of numbers. The top is 1, and then the next two entries are 1 and 1. And then the way you get all the subsequent rows is you're always going to get 1s on the outside, and then 1 plus 1 gives me 2. And then 1, and then 1 plus 2 is 3, 2 plus 1 is 3, 1, and so on. 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and so on and so on and so on. If any of you ever take a stats class and you start talking about the choose function, come see me and we'll talk about it, because this triangle is intimately related to the choose function, of the number of ways of picking so many things out of so many things, which you see in stats 13 or stats 100 typically, or a probability class. Or in actually at the very end of 17C. So at the very end of 17C, where you do some probability stuff, come see me either in the summer or fall, whenever you take 17C, and I'll remind you of this because it's kind of a cool way of seeing a small part of that. But for now, check this out. So I'm going to point out a few things that might seem silly to write, but I'm going to write them anyway. X plus h to the 0th power is 1. Okay, not very exciting. X plus h to the first is 1x plus 1h. X plus h squared is 1x squared plus 2xh plus 1h squared. And what I'm trying to imply by writing it this way, which is true, is that the numbers in each row of Pascal's triangle give you the coefficient of the expansion of x plus h to that power. So I typically say that my top row is my 0th row. And then we have the first row, the second row, the third row, and so on. The third row gives me the coefficients of x plus h cubed. It's going to be, now here's the pattern. Here's how the pattern always works. The powers add up to whatever that initial power is. In the second one here, x squared or x to the first, h to the first, 1 plus 1 is 2, or x or h squared. The powers add up to 2. In this next one, the powers are going to add up to 3. We always start with the highest power of x, and then every next term, we lose a power on x and gain a power on h. So this one's going to be x cubed plus 3x to the 1 less, h to the 1 more, plus 3x to the 1 less, h to the 1 more, plus 1 x to the 1 less, h to the 1 more. So x plus h cubed is x cubed plus 3x squared h plus 3xh squared plus h cubed. And you could even use it for x plus h to the 4th if you needed to. X plus h to the 4th power should be 1x to the 4th plus 4x to the 3rd h to the 1st plus 6x squared h squared plus 4xh cubed plus 1h to the 4th. I think this is worth remembering. Instead of having to actually multiply out x plus h times x plus h and then FOIL that with another x plus h to get x plus h cubed, you can remember this pattern instead. And it is called Pascal's triangle. So back to the problem we were doing, we can then say that this is equal to limit h approaches 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all divided by h. Another thing I also would point out is that whenever you're doing x plus h to some power, your first term is x to that power, your next term is that power times x to the 1 less power times h to the first, right? It's always that number coming down as your coefficient, like you see, right? It's always a 4 there, then right. The second term is always going to be just whatever the same number is as the power, because you just always add 1 to get to the next row. And now the usual types of things happen. The non-h terms cancel. The x cubed minus x cubed is 0. Every remaining term has an h in it, so we can factor out an h, and we're left with 3x squared plus 3xh plus h to the second divided by h. The h's divide to 1. We're left with a limit as h goes to 0 of 3x squared plus 3xh plus h squared, which is going to be 3x squared plus 0 plus 0. So the derivative of x cubed is 3x squared. In a similar way, we can show that for f of x equal to x to the fourth, that our derivative is going to be 4 times x cubed. Let's take a look. Yeah, we have enough time. So the derivative is going to be the limit as h approaches 0 of x plus h to the fourth power minus x to the fourth divided by h. Using Pascal's triangle to multiply out that x plus h to the fourth, we're going to get x to the fourth plus 4x cubed h to the first plus 6x squared h squared plus 4xh cubed plus 1h to the fourth minus x to the fourth, all divided by h. And the same sort of thing happens, right? The non-h terms, the x to the fourth and the negative x to the fourth, add to 0. The rest of the things have an h. We factor it out. And here I'm going to point out something additionally. Every term except for this term that I just circled, every other term has more than one h. H squared, h cubed, h to the fourth. Meaning, when I factor out an h to the first, each of those 3 terms is still going to have an h left in it. And then when we let h go to 0, all those are going to go away. So we're just going to be left with this. So this second term here of our expansion is really the only one that matters. So when we write this out, factoring out an h, we have a 4x cubed plus 6x squared h plus 4xh squared plus h cubed divided by h. The h is divided to 1. We're left with the limit as h goes to 0 of 4x cubed plus lots of terms that have h's in them. So all these terms, oops, these all have h. They're all going to go to 0. So we end up getting 4x cubed. And the same sort of thing would be true for the next power, right? If it was x to the fifth, it looks like our derivative would be, well, our second term would be 5x to the fourth h, and so that's the thing that's going to tell us what our derivative is. So this is leading us to the power rule, which is that if your function is x to some power, your derivative, and we will show this next time, is that power times x to the 1 less power.